Okay, thank you very much for the organizer to inviting me to give this lecture. And well, this conference is more or less also a tribute to Gilles Lachaud, and the next two speakers will talk more about it, but I like to tell also something about Gilles Lachaud. It's not that I know him well personally, and I've never cooperated with him, but I've been here at this conference 6 times before. The first conference I attended, AGCT, was in 1989, and the next 4 I also attended. And so what I like to do, give some history from my personal perspective on algebraic geometry codes. And okay, so I will, for that part, I will use the blackboard. So, and what I will explain some history about algebraic geometry codes, and in particular about what happened and how this tower of Garcia-Stichtenot was invented, or how it came, or in fact it was more or less an accident. And that part I like to explain or tell. And Al-Bassa explained very nice lecture yesterday about the mathematics, and he mentioned my name, but my name is only for a very small part, and the part is that I changed the 3 into a 2. I will explain that. So some history. So like the first AGCT was in 87, I think, and so the prehistory is Goppa invented the codes using algebraic geometry, curves over finite fields, and you had the Strassmann-Flooded thing result, Ihara, things like that. And so then that was the Gilbert-Fashemoff bound was beaten for, well, larger field sizes, but okay, these codes were there, engineers were impressed, in particular the electric engineers, the IEEE community. They said, well, okay, well, that's nice, but can we understand it? Well, that was a problem. And a lot of mathematics, deep mathematics was involved. And so there was another thing. These codes were invented, they were there, but there was no decoding algorithm. So when I started in Eindhoven, Technical University, people were very much interested in the topic, but they had not the right background. So I came from singularity theory, applied for a position, I was hired, and but I didn't know anything about coding theory or about combinatorics. So, but I was very lucky because at that time, 87, 88, the first decoding algorithm was proposed, and by Danish people, Justesen, Tom Heult was involved in that. And then later it was, that was for plane curves, and Skoro Bogatov and Sergej Vladuc, they generalized it for arbitrary curves, and so that I could contribute there in this direction. And so that's, I think, the reason I was invited for the my first AGT conference. But so you had this decoding up to, well, that is the designed minimum distance of the AG code, and well, that's the number of errors you want to correct up to half the minimum distance, or half the designed minimum distance, but there was a G involved, and it's not the best you like to have, and so I contributed there something, but it was not effective. I mean, but you must understand that you had these two communities. Algebraic geometry, I say, call it AG, and you have, say, coding theory, and well, this is, say, deep mathematics, and this is the IEEE, the engineering community, where, well, they really use codes, it's really implemented, and so that is very applied. And so we live in here, in this intersection, which I called AGC, algebraic geometry codes. And, and this community was, well, okay, we can apply it, forget about that part, the application, we continue on this topic. And this community said, well, okay, this result is there, but we like to understand it. And, well, that was a problem, as I said before. And then there was a movement that said, well, AG codes without algebraic geometry. So I put a banner here. That was really a movement. And it said, well, that's stupid. Why would you do that? Just learn algebraic geometry and then, well, then you are 10 years further, of course, but so, well, that was really a movement. One of the persons was Bleihut, and he advocated that. He really gave lectures with this title, and well, you understand, I'm in a technical university, and the background here, so I was really in the middle. I tried to explain what was going on there, but yeah, well, what was their background? So I was really, well, interested in accomplishing that. So, okay, what happened then was you had Feng Rao. They came with a decoding algorithm, majority voting of unknown syndromes. So let me mention it. And the result was they could really efficiently, effectively decode up to half the designed mean distance. And it was a very nice idea. The only problem was the paper was as follows. They had an elaborate example and showed how the algorithm worked. And then they stated the theorem, and the proof was, see example. Well, mathematicians are not satisfied with this. And then was, I showed it to Ivan Deursma. He was working on his PhD, and he came up with the proof. So I can say the idea is here, but he gave the proof. So of course you need both, and but that was because it was so basic, and so Feng and Rao they heard about this slogan, AG codes without AG, so they continued, and what out of this decoding algorithm, usually if you have a decoding algorithm, you can say, well, look better at it, then you get a bound on the minimum distance. And that came out, that is the Feng Rao bound, or the Orderbound. And that is, you can phrase it in a very general terms without using any algebraic geometry at all. So that was already a step. And in trying to attain this goal of AG codes without algebraic geometry. And then he came with another step, again Feng Rao, and what he did, is the following. Again, his idea. Say, look, you have an equation, and this is the equation. So that is a well-known Klein curve, and that is over F8. And it has, you can easily see if x is non-zero, then you have 3 non-zero solutions in F8. So that was the idea. So what is the idea? So you get a tower. And so you have, well, it's given by in the variables. And you use the same equation, but you shift the two variables xi and xi plus 1. And that is for i's 1 up to m minus 1. And then, of course, by this remark, for every non-zero x, you have 3 non-zero y, so you have, of course, the number of points of F8 is at least, well, you start with 3 and, 7 times 3 to the power m minus 1. So that idea is really his, or theirs, Feng Rou, and then he used this order-bound kind of argument, very explicit, to show, well, he claimed that to get asymptotically good codes. No algebraic geometry involved, except then, of course, this equation, but no Riemann-Roch, no modular curves, nothing. But of course, when I saw this result, I said, well, okay, that's nice. This grows fast, and he claims that the parameters are giving asymptotically good codes. But of course, I was interested in the genus. What happens with the genus? What is the genus? So my guess was it grows much faster than the number of points, and I knew of a result of Henning-Stichtenot and Frey and Ruud, a negative result in a certain tower of function fields. Then this quotient of numerational points divided by the genus, that goes to 0. And so it's asymptotically bad. So I sent an email to him. And oh, it's nice. I mean, his story, and I still have the emails, and they are of August 1994. So 9 August 1994. I sent an email to Henning-Stichtenot.
You mean 98 or 94?
Sorry. Yeah. Thank you. And it appeared that he was in IMPA, in Rio de Janeiro, in Brazil. And I asked him the question, say, well, look, you have this negative result of towers, and can you tell me whether that applies here? And then he said, well, look, I worked very hard with Arnaldo Garcia, and I want to have a 2 weeks vacation in Brazil. But okay, well, my first guess is I think not, because, but it's difficult, because it's not a Galois extension, and it's a wild ramification. So, okay, and but well, he was thinking about it, and so 2 weeks later, so he tried something like this, an equation. Well, it looks not like a polynomial equation, but for him it's always function fields. So that is just defining the extension. recursively, but did not work. So I did this as negative result. At least he could show, in this case, that it doesn't work, that you get asymptotically bad tower. So, so let me see. Well, I can put here 29 of August, the same year, and then the next day, so well, look here.
What is the tower? What does that mean? That
Sorry?
last line you wrote?
Sorry?
What does it mean, the last line you wrote? What is the tower?
Okay, so the idea is you have a polynomial f in two variables, right? And then you do this. And then the question is, which f should I use in two variables? So Venro used that f, the Klein equation. And then Techno tried this one.
Oh, you mean the difference is the rational function?
Yeah, so, yeah, right. Yeah? Okay, so, and at least he could give a negative result, but of course it didn't answer my original question. So, but then I said, well, okay, what about this? And here comes the change of a 3 and a 2. And now, here also, the 3 is changed in a 2. Why is that? Well, just for a simple reason that here you have, for every non-zero x, you have two solutions which are non-zero, and here over f8, and here over f4, for every non-zero x, you have two solutions y non-zero. And that's the only reason, and I expected a negative result, right? And that's only, if a problem is too hard, you make it simpler. That's the only reason. And then try to solve that problem. And then, the next day, he said, well, I think this is a positive result.
Your equation, is it
Sorry?
the second y squared, should it be x?
No, this one, with this fi, he had a positive result. One,
Look, well,
yeah?
is it not xy squared plus x squared plus y?
Oh, yes, of course, yes. That's important. And, yeah. So, yeah, sorry. Thank you. Okay, now it's correct. So, I think plausible positive result. And in the next email, he even said, well, the general result, I have a general result, together well, we think of a general result here. You couldn't prove it at that time. So let me write it correctly. Huh? Over, and that is so let me quote now. It's in German, but I will translate. So, wir haben eine anstrengende Woche hinter uns. So I translate and continue in English. We had a demanding week behind us, but I believe it was worthwhile. The sequence is indeed asymptotically good, and it even attains the Dirichlet bound. That is, the number of points divided by g goes to q for every fq squared. So that is the history. So I ruined his vacation, but we have a really wonderful result, and it's really a miracle how this happened. So far, this history, and yes, and that is my tribute to Gilles. And Oh yes, I should say also. For me, Gilles is, if you think about algebraic geometry codes, for me it's located here in Lumini. And it's really the center, for me always has been the center where the action was in algebraic geometry codes. And I think that we can attribute this to Gilles Lachaud. Okay. Now my lecture, I spent some time on Gilles, it's important, and I don't know whether I can explain everything here, but that is not so important. The main message I want to convey here is that, well, the weight enumerator, there is some theory, and I think we understand it more or less. It is hard to compute the weight enumerator. Whatever way you do it, it's hard. But the coset leader weight enumerator is much harder. It's much harder, and there's not much known about it. And so for a conic, you can compute it. Even for the twisted cubic, it is you must analyze it in very much detail to get the result, to get a close result. And for that, well, I should mention that is joint work with Art Blokhuis and Thomas Söhni. And we use the classification of twisted cubic, the projectivities of the twisted cubic in the rational curve, normal rational curve in P3 of degree 3 by Bruin and Hirschfeld. And I thought, well, I did this for the conic, the coset leader weight enumerator with Relinde Jurius. And I thought, well, let's ask Art Blokhuis, he's my colleague in the same corridor, about the twisted cubic. He knows everything about the twisted cubic. And he thought so too, and I said, well, but it turns out to be a very interesting, demanding, and well, you really have to go deep into the details of this classification of Bruin and Hirschfeld. So, first some elementary things we all know. So, FQ is a finite field. The weight of a vector is just the number of non-zero entries. The Hamming distance is the number of positions where two vectors are different. The difference between two x and y is the weight of the difference. I mean, you have the NKD sub q code, that is an FQ linear code of dimension k in FQ to the n of minimum distance d. So that is the minimum distance between two non-zero code words. And it's for a linear code it's the same as the minimum weight of a non-zero code word. And then you have the notion of a degenerate code, and that is important in the sequel. A code is degenerate if there is a position where all code words are zero. Well, they say, well, that's not so interesting, just throw away that position and shorten it. You cannot possibly use that, but for arguments, that's of course important that they are there. So, okay, so we have the generator matrix of a linear code that is of dimension k. It's a k by n matrix such that the rows generate are a basis of the code, and of course you can write it as the null space of a parity check matrix. That's the H. Okay, so we have the inner product, well known, the standard inner product. You have the dual code, which all vectors which are perpendicular have inner product zero with all code words, and the generator matrix of a K of a code C is the parity check matrix of the dual code. So now we come to the notion of the weight enumerator. So the AW is the number of code words of weight W. Yeah, so, and then we can put them just in a polynomial, whether you do it in one variable z or homogeneously in two variables x and y. I prefer this one. We come to that in a minute, where it's comfortable to have it in this way. And well, for every w which is positive, if you have a code word, non-zero code word, you can multiply it with a scalar, non-zero scalar, you get again a code word of the same weight. So every AW for W bigger than 0, the number is divisible by Q minus 1, and then I divide out by Q minus 1. In a sense, you consider the problem projectively, and the AW bar is the number of, say, the projective points. So why are people interested in the weight enumerator? Not only as a mathematician to classify, because of course you get a crude classification of codes, but it has a probabilistic interpretation in a Q-array symmetric channel with crossover probability small p. Then this term is of course the number of code words, or the probability that a message sent is without errors. And then you have this, and that is, if you subtract that, then that's the probability that at the receiving end you have an undetected error. So if a code word is sent and on the receiving end it's again a code word but different from the original code word, you will not detect it because you say, well, it's a code word, it's probably the code word sent. Well, there is some probability that this happens, and that is you can put it, or you can compute it in terms of the weight enumerator. There's another thing you can compute. So if you have a bounded distance decoder, so you decode up to, say, half the minimum distance, and then these spheres around the code words, that is the part where you decode. So if this is sent and that is received, then the decoder will give you the correct code word. But what can happen if there are a lot of errors, then it will send it to a closest code word, but it's not the one you have sent. And of course, there's an area where, well, the decoder can do nothing because it's outside half the minimum distance. So then you have a failure. Okay, so this is a very complicated formula. Again, in terms of the weights here, and this is the crossover probability, and this is a combinatorial number. I can also give a complicated formula in terms of binomials, but it is just the number of vectors in FQN of weight W that are a distance S of a given vector of weight V. And this given vector is independent. I mean, you can choose anyone. You can choose the, well, any vector of weight V. Okay, just to assure you that it has an application and engineers are interested in it. Okay, so what I will do in the following is that I look not only at the code, but also at the extended code. So extended by scalars. So I use this notation, the tensor product of the extended field, the field extension of degree m. And well, it is just the same code, but with the scalars in FQM. So if you generate a matrix with entries in FQ, you can use the same generator matrix, but then the coefficients are now allowed to be in FQ to the m. So that is the next remark is stated here. And so now I come to a topic, the weight enumerator of the of a code in terms of arrangements. And well, of course, there's some finite geometry involved in here. There's a lot of finite geometry because it was already well known that the connection between codes and finite number of points in projective space, right? And that is more in the sense of a projective system. In a small paper by Kasman and Solomon, which appealed very much to me when I have read it, and you find it also this idea in the book of Solomon and Vladet, a projective system. It's just a number of points, an n-tuple of points in projective space of dimension r, but the only assumption is that they do not lie in a hyperplane. So, and if you have a generator matrix of a non-degenerate code, that means all the columns of the generator matrix are non-zero, so you can view these columns now as projective points in projective space of dimension k minus 1, right? And in this way, you get a projective system associated with the generator matrix. And conversely, if you start with a projective system, you can make the, you use the coordinates of the points, but now as columns in a generator matrix. You get a k by n matrix, and by this assumption that they do not lie in a hyperplane, the rank of this matrix is k, and so you get an nk code, right? And then you say, well, what is about the equivalence? You have the generalized equivalence of codes, and you have projective transformations of the projective space, and you can permute the points. So, in fact, these two theories are equivalent theories. And then the question is, what is the minimum distance? How do you express the minimum distance? So if you have a code word, you can write this code word as, say, a message times the generator matrix. This message lies in fq to the k, and now you consider the hyperplane with the coefficients m1 up to mk as coefficients of the linear equation, the homogeneous and linear equations. And then you have the number of points in, of this projective system that lie in the hyperplane is equal to the n minus the weight of the code word, right? So you have a very nice interpretation in terms of projective system of the mean distance. And of course, you can say, well, what is AW? And now I consider this hyperplane over the projective space. It's the number of hyperplanes in the projective space of dimension k minus 1 with exactly n minus w points of this, oh, that should be G there, of the projective system of the generator matrix. Okay, well, that's nice. But dually, you can, well, okay, so that is also an important remark. You have the notion of, well, suppose we have a non-degenerate code, and an MDS code, that is a code that attains the singleton bound, so that is an n minus k plus 1 code, well, the largest minimum distance you can get according to the singleton bound, and that is an MDS code if and only if the points of the projective system are in general position. So that's to say there are at most k minus 1 points of this projective system lying in any hyperplane, right? So, well, these kind of things were well known. Finite geometry people and arcs, and that's another terminology involved in there, but you have this translation, that's well known. And, but dually, you have an arrangement. So instead of points in projective space, you lose linear well, hyperplanes in projective space, or you can also consider it, I do both in FQK, and I assume that it is what people call an essential hyperplane and central, but I just, I call it an arrangement if the intersections of all these hyperplanes in FQ, if you consider it here is the origin, and here then it's empty. So in here again, you have the generator matrix, the coefficients of a column corresponds with an homogeneous linear equation of a hyperplane. And in this way you get n hyperplanes and you put them in an n-tuple, and that's the associated arrangement of the code. And again, conversely, you can start with an arrangement over a finite field and you have a code. These are, again, of course, equivalent theories. And here you also have, what is the minimum distance? Now, n minus the weight of a code word is equal to the number of hyperplanes of this arrangement going through this point. And now this point is considered as homogeneous coordinates, right? And again, the dual statement is AW bar is the number of points in the projective space such that n minus W hyperplanes, exactly this number goes through this point. So now picture. So you have these two dual pictures. So this is the projective systems. That means these 4 points, and they are now in general positions. And you see, well, the maximum number of points on a hyperplane, here a line in the projective plane, is 2. So 4 minus 2 is 2, so that's the minimum distance. And so it's in the plane, so the dimension of the code is 3. And dually, as an arrangement, you have now the 4 lines, the 4 hyperplanes. And you see, well, what is the maximal number of lines going through a point? That is everywhere 2. So indeed, again, of course, the minimum distance is 2. And from this picture, it is easy to compute the weight enumerator. Of course, this is a very simple example just to get the idea, but you will, I'm sure that after this lecture, you just draw any line arrangement and you compute your weight enumerator from there. That is an exercise you can do. And so in particular, the AN, so the length of the code is n, and I view it now projectively, AN bar, is just the number of points in the complement of the union of the hyperplanes of the arrangements. And of course, that is computed also by people using a zeta function of this complement of the hyperplane. And and then, well, you see the principle of inclusion exclusion. It's computed is just the number of points in the projective space, and then this number you have to compute. That is an alternating sum. If W is 0, it's the whole space. That's the empty intersection. And if it's from this you immediately can compute what the number is if the hyperplanes are in general positions, because then this has dimension n minus w, and you have n choose w ways to choose it, so you have a closed formula for that. It's easy, we will see it in a minute in another way, but that is the idea for AN, so the maximal weight n number of code words or projectively seen in this way. Okay, so there is some technicalities involved, and I go quickly through it, well, that you find in the paper of Kastman-Trostman, and you just look at the space CG of the code words which are 0 at a certain set J, and well, that is, now here this intersection is not seen projectively, but in a vector space, and this intersection is as a vector space. These are two isomorphic, and then you compute the dimension, you compute the bj here, it is the q to the power lj, and the bt is the sum over all subsets j of the bj's. And I quickly go through it, and well, there is this extended version. Instead of over FQ, we want to look at it for the extended code, and we introduce an extra variable, because look here, if you compute this for Q, well, what you in fact do, you compute this for all subset J, and that's just linear algebra, computing a rank of a matrix. And if you've done that, then you know the weight enumerator not only of FQ, but for all extensions. And that turns out to be so. And so that's why instead of the Q, I use the T. And if you put the QM in there, so you get the weight enumerator. So this is, you get the following relation between the BT and the AW. And of course, they determine each other. And there is a minus sign gone. It should be alternating sum. I have to correct that, sorry. Okay, but anyway, this is an important result. That the weight enumerator is now in terms of this BT, and you have seen this BT is just computing these dimensions of subcodes which are 0 at certain positions. And for the extended version, you have the T involved here, and just computing these BT, computing these dimensions. And so indeed we have, if you look at the number of code words of the extended code of FQM of weight W, it's just putting in T the Q to the power M. right? And that is this formula here. And well, in a sense, this is a motivic version, because for the weight enumerator you count the number of points, and then it should be finite to get a number. But in this version, there is no counting of points; it's counting of dimensions, and then you can your field of scalars can be any field, right? Okay, so. Right, so here I think that is the right version with the alternate sign. And this is, well, the MDS code, the number of code words of a fixed weight W is given by this formula, and for the extended version, it is this formula. And we, in a sense, we have seen that already in this inclusion-exclusion slide. Okay, so here you can compute it. So for this simple example, so A1 is of course 0. There is no point lying on 3 lines. There are 6 points lying on 2 lines. So that is here. So I compute the projective version. So that is 6 points. And then you have 4 lines. And on the line you have to exclude these 3 points, so that is t plus 1 minus 3, that is t minus 2. And then you have always, if you computed 2 of them, then the sum is the total number of points in the projective space, that is t squared plus t plus 1. Well, it's hardly visible, huh? So I erase it. So A1 is 0. There are no 3 points on, there is no point on 3 line. There are 6 points, the red dots, right? So that is the arrangement explanation, on 2 lines. So 4 minus 2 is 2. And then you look at the points which are exactly on 1 line. So there are 6 lines, and then, but you have to exclude these 3 points on every line. So that is, you have 4 lines, and then t plus 1 is the number of points on a projective line, and you have to exclude 3 points, so that is t minus 2. And then I say, well, the A1, well, the bar, that is the number of points on the projective line, the projective plane. And from that, so if you have the last one, you never have to compute because you have this relation. Okay, so I hope you understand this. And then in your favorite example, if it's a 3-dimensional code, you draw the picture and you can do by hand compute the weight enumerator and even the extended weight enumerator. So now just give an overview of the connections. So we have the extended weight enumerator. Well, there's also this notion of the generalized weight, that is considering subcodes of a certain weight, and that is not over the extended version, but for all R, for all possible subcodes of dimension 1 up to k. That gives the generalized weight enumerator for all R, and this set of polynomials, they determine each other. So this gives the whole sequence, they all determine each other. Then Green gave the connection of the third polynomial of a matrix in terms of the weight enumerator. So you have a code and you have the you have the matrix of the code, and that determines the third polynomial, the dichromatic, the binomial third polynomial, and that determines the weight enumerator. And it goes both ways. And you have also the notion of the co-boundary or two-variable characteristic polynomial of the geometric lattice. Geometric lattice of matrix is almost the same. And then you have the so-called two-variable zeta function introduced by Ivan Duursma. and they all determine each other. So there's explicit formulas going from one to the other, and that is all you can find in the PhD thesis of Linda Urius. And well, of course, well, not of course, but the ordinary weight enumerator is really weaker invariant than the extended weight enumerator. So why do I tell this all? Because I want to talk about, in my last 5 minutes, about the coset leader weight enumerator. Because that is, because you have to understand it first, the approach in terms of projective geometry, and then the projective system and the arrangement both show up. You have to use them both. And you have to use the projective system, and now not of the generator matrix, but of the parity check matrix. So I give a rough outline because I have not much time. You have now, you use not the generator matrix, but the parity check matrix. You consider the columns of this, and that gives a projective system, right? And but what is the weight of a coset? That is just, in this coset, you look at the minimal weight of an element in this coset, right? A coset leader is an element, a choice. There might be many, but you just choose one of minimal weight in this coset. That's called the coset leader. And then instead of A, we use now alpha I, the number of cosets of a code that are of a given weight I. And then you can put this number again, in a polynomial, the homogeneous version, and okay, that's called the coset leader weight enumerator, the coset leader. Okay, so why do people consider this? Because it computes some probability. The main probabilistic thing you want to know as an engineer about the behavior of a channel with a given crossover probability. First, you have a coset leader decoder. You have first the preprocessing. That's one way to do it. You have just a list, a memory of all coset leaders. You have a received word. Then you look for this received word, what the coset leader is of this coset of the received word. You subtract this coset leader, and that is your answer. Yeah, well, you know it's a code, and also that the distance of this code word to the received word is the weight of the coset leader, which is the distance of the received word to the code. So this is indeed the nearest code word decoder, but of course it's not necessarily the code word send, and you can have decoder errors. But this is the important property in a Q-array symmetric channel with crossover probability small p, you can compute the probability of decoding correctly, and that is in terms of this coset leader weight enumerator. So that is, in fact, hardly know any examples, well, trivial examples, but how did they compute it? They simulate the channel, and then they computed so really, general results are hardly known. Of course, the alpha I is this number for up to half the minimum distance. There's a unique coset leader. Of course, if you go beyond the covering radius, by definition, this alpha I is 0, and the number of the this number is just the number of cosets, right? Okay, so just one simple example, trivial example of the dual of the repetition code. So that this is the parity check of the code. So that is a code of dimension n-1 and minimum distance 2. And well, what is the, we can choose coset leaders of this form, lambda 0, 0, 0, and then lambda arbitrary FQ, but of course you could have chosen the second position also. So there are a lot of choices of this coset for a coset leader of a coset, and here it's easy to compute the coset leader weight enumerator of this code. But the next example is already not so trivial, although the code is very easy to describe. You consider the product code of two codes which I considered before, CM and CN, and the code words are now seen as matrices, m by n matrices. And the condition is that the sum row is 0 and the column row is 0. These are the parity checks. And that's all. That defines the code of all code words are now in the space of m by n matrices. And these are the parameters, length m times n, dimension m minus m times n minus m, minimum distance is 4. What is the coset leader weight enumerator? Well, for QS2 and QS3, Putranto Utomo did that in his PhD thesis. It is already quite complicated combinatorics involved, but, well, it's an open question to do it for arbitrary Q. So that's exercise for you. At the end of the week, you have the answer of this. I challenge you. It's much harder than you might think at first. But I hope someone is clever and gives the right way to look at it. That's my hope. And that's in fact my hope of this whole lecture, that people consider it and come up with new ideas to tackle this coset leader weight enumerator problem. Well, again, what we did for the weight enumerator, you can say, well, what about extending the code and then looking at the coset leader weight enumerator of the extended code? And then you have the alpha I q to the m is then by definition the number of cosets of the extended code of weight I. And of course, if I is bigger than 0, then you consider it as a polynomial. You can show that there exists such a polynomial that is a unique polynomial and that is divisible by t minus 1 again. And the alpha I bar of t is then the alpha I t divided by t minus 1. And you have the extended coset leader weight enumerator of the code. And it is this polynomial in x, y, and this t. And okay, so at least I should explain what the geometry is in terms of the parity check matrix. And I think I should end there. And then, so if you have two cosets, then the difference is a code word. So, but this term is called the syndrome of R1, and this is syndrome R2. So the syndrome of a received word determines its coset uniquely. There's a one-to-one correspondence between cosets and syndromes. Okay, so now we have a parity check matrix, and so I suppose that it's not degenerate, so there's no 0 column there. And well, and then the weight of the syndrome with respect to H, if you take another parity check matrix, the weight can be completely different, but we fix the parity check matrix, and the syndrome weight is then the weight of its correspondent coset of the received word. And well, what is now the geometry or the linear algebra of this? The syndrome is a linear combination of columns of the parity check matrix. And the syndrome weight is the minimal way to write a syndrome as a linear combination of this parity check matrix. So in this way you can compute the number of vectors that are in the span of I columns of H and not in the span of less columns, right? And now we are in business to compute the coset leader weight enumerator or the extended one. But mind you, in the projective system of these points, so this defines a code. These 6 points define the code. And the matrix of this one and this one, they are the same, right? So in the case of weight enumerators, you say, well, it doesn't matter, it's enough information to compute the weight enumerator or the extended weight enumerator. But here, you have a problem because these lines, 3 lines go through 1 point in this case, but they don't in this case. And that gives a completely different answer for the coset leader weight enumerator, right? So these 6 points are the number of points projectively seen of coset leader weight 1. And of 2, then you look at the line connecting 2 points, and they should be on this line, not but distinct from these 2 points. And then you compute, so there are well, that you see here. So in this case, all connecting lines have 3 points, but yeah, here, this is a coset leader, corresponds to the coset leader, but in fact, there are 3 choices, right? These 2 points, these 2 points, these 2 points, giving 3 possible choices of coset leaders. In this case, there's not such a case. So it gives a completely different answer. So what we, Julius and I did, that well, you have in geometric terms, you have a projective system, and then you look at all points in general position, you connect them, it gives a subspace, and you get, in this way you get an arrangement. And this arrangement is, we call the derived arrangement. So it's really the projective system sitting in the derived arrangement, so these lines, that is the derived arrangement, they are different, and that gives you a way, well, theoretically, to compute the coset leader weight enumerator. Still complicated, but well, there is a theoretical formula for that. So I should skip here a lot of slides and more or less to what I promised in my abstract for the coset. Sorry. Well, I want to tell something about Gilles and the history of AG codes. Okay, this is so there's a lot of straightforward things. You have a twisted cubic, rational normal curve in projective space 3 of degree 3, and then depends very much on Q what the answer is. There is a number which we call lambda Q or mu Q, and depending on Q being the value 1 modulo 6, what the answer is. And as I said, you need for this, you need the classification of Bruin and Hirschfeld, and then go into that very deeply, or, well, you have to check it meticulously, and it's not straightforward. Okay, so, as I said, computing the weight enumerator is hard, the coset leader weight enumerator is even harder. Already in the twisted cubic case, well, that is a genus 0 curve, right? So, but it should be simple. It's not. And for a degree larger than 3, I really don't know. And this classification, it's not known for R's bigger than 3, as far as I know. And so I think you should have other ideas there. So new ideas are needed. It's up to you. Hopefully you will contribute. And I thank you very much for your attention. Yes?
You have the result on the direct product of 2.
Yeah, it's known.
Because what is known, the covering radius of this code for Q equal 2
yes.
is a so-called Gale-Berlekamp problem.
Okay.
And is known to be very difficult.
Yeah, so, but you have this code and the dual of this code. So right. I've seen something like that, but I think you're referring to the dual code. But, well, let's talk about it. I'm interested what you have to say about that. Thank you.
I think we should thank the speaker.
Yeah, you're welcome.